In our last videos, we focused on incompressible fluids. This condition can be assumed in most practical applications for liquids. But there are important exceptions, as in the case of water transients in closed pipes. Water hammer is the typical example. Gases, or vapors, by their own nature are compressible. And we live immersed in the atmosphere, which is formed by compressible gases. So there is no escape. We must know what happens to them. We saw that when the fluid is incompressible, ρ is constant and the integration is simple. These are the results of the integration. Observe that P0 is the pressure on the horizontal plane used as reference, which we call ballon. Its elevation is 0. In the study of compressible fluids, we must know the variation law of ρ in relation to z. In the atmosphere, we must consider two different cases. What happens in the troposphere, which goes up to 11 kilometers high, and what happens in the stratosphere, which lies above it. Well, the exact altitude in which this transition occurs from troposphere to stratosphere is not well defined. It depends, among other factors, on the latitude and on the year season. When we consider the elevation limits, which are important to engineers, 20 kilometers, where the cirrus clouds are formed, they're the highest clouds, temperature in the stratosphere is almost stable, around minus 56 degrees Celsius. That's why we call it isothermal atmosphere. First, let's notice what happens in the troposphere. We introduce the atmospheric vertical thermal gradient, which shows how temperature varies as we move up through the atmosphere. If we substitute dz in this equation, we find this relationship. Gass's law states that P over ρ equals GRT. Let's rewrite it in this form, or in this form, which is better. When we substitute it in the upper formula, we find this. Let's rearrange it for integration. Integrating between the limits 1 and 2, we find this expression, which leads to this and this one. Let's write it again. This is the expression that we wanted. It's possible to check if it obeys the polytropic equation, P over ρ to n equals constant. This is the gases law, that we can rewrite in this form. We find this for T1 and this for T2. Substituting the values of the temperature in the upper expression, we find this, which we can simplify to this. It can be simplified a little more, or even better. Look how cute it's looking now. Now it's almost perfect. If we call 1 over 1 minus lambda r equals n, we arrive here where we wanted. P over ρ to n equals constant. For the atmospheric air with r equals 29.3 meters per Kelvin, the n values corresponding to lambda values between usual limits are shown in this table. The practical value that we use in most cases is n equals 1.4. It's not too hard for us to find the relationship between elevations and pressures. From the equation, the P over ρ to n equals constant, we can write this. Let's assume that we know the values of P and ρ at point 2. In this case, we can write this expression. If we use it with the gases law, we can write this new expression. We can integrate it between 1 and 2, and this is the result of the integration. And this is the expression that we were looking for. Also, it's not very hard for us to find the relationship between elevations and temperatures. We can do it from the definition of atmospheric vertical thermal gradient. We integrated between 1 and 2, and this is what we obtain. but n equals 1 over 1 minus lambda r. Then we will write in this form. This one is much better, and here is what we wanted. Now the stratosphere. Up to the elevations of our interest, we assume that the temperature is constant. So, the atmospheric vertical thermal gradient lambda is 0. Thus, n equals 1. And this expression represents the isothermal process conditions. Let's go back to the dP versus dZ equation. Since n equals 1, the polytropic transformation law for gases becomes this one, P over rho g equals RT. If we call T1 the constant temperature that prevails in the stratosphere, then we can rewrite the former expression in this form. Now, in this form, it's ready to be integrated. It's easy to do it. This is what it looks like after integration. Let's rearrange it. If we call Z2 minus Z1 equals H, the expression looks nicer. Okay, there's still room for a little more algebra. We can use the Taylor series for e to x in this expression. Now it's easier to use. Or, knowing that P over rho g equals RT, we find this new relationship, which then turns into this. Just take a look at it. Now, this expression is very important to us. It shows that if we can assume that the temperature is constant, even in troposphere, and for not very large elevation differences, we can assume that the atmosphere is incompressible when we calculate pressure differences in it. We've already talked about this in another video. I'll leave the link in the description. Whoa, so much algebra! It won't always be like this, I promise. But the approaches for this subject that we find in the literature are usually so hard to understand. So I try to make it easier here. What is your opinion? I'd like to hear your comments about it, so I can improve in my next videos. That's the whole point, to explain fluid mechanics with clarity and simplicity. In our next video, we'll talk about devices for pressure measurement. See you there! Oh, and if you like this video, don't forget to give it a like, comment, share, and subscribe. Hit the bell so you can be notified of my next videos.